Well, hi. It's still good morning. Thanks a lot for joining me here. I'm going to be looking at three molded capacitors in this radio. One of them is jumping out at you here. A very similar one is buried down under here. This radio's not on, by the way. I'm sticking my finger in it. Well, we're going to start with this guy here, which sometimes is referred to as a bumblebee capacitor. Let's take a little closer look at it. There he is. Now, the first thing that grabs my attention about this is there's too many bands on it, too many colored bands on it. Yellow, mauve, orange, looks like dark blue or something, maybe black, where there appears to be nothing, and then an orange. What are all those bands doing on there? And the other thing that I kind of caught my attention about this is at the bottom where the lead comes out of the capacitor body. It seems to come out and then get attached to, see, it comes out wider, you know. So, hey, is this thing actually a coil? You know, I don't think so, but I'd be foolish at this point to just cut it out. What I want to do is identify where this is in the circuit, and then we'll know for sure what it is on the schematic. And I can do a couple of tests on here, quickly prove whether it's a continuous coil in there or just a capacitor. So, okay, so how am I going to figure out where this guy is? He's connected. See, one lead comes down to a terminal strip where it encounters a couple of resistors and looks like some other stuff in there. Another resistor up tucked way up under there. So that's a pretty hard spot to identify, because on the schematic, all those components aren't necessarily all tied to one point. They could be strung out along a line that travels through the whole schematic. So that's not an easy way to figure it out. Now we look at the other end. Wow, it certainly is going to ground. That strongly suggests a capacitor. There's the other one, the green one down there that I'm going to be going after next. So one end's to ground. That doesn't help either. So we're really stuck with trying to identify it from this end. So we'll pick one of these resistors. Let's say that gray, red, yellow one there, and it goes to another terminal strip. So that's just lost in the circuitry. It'd be really hard to find all this stuff. And I don't know the value of this capacitor. I'm not going to try to interpret those bands. I can certainly see the value of the resistors. There's a 1 million there. Oh my gosh, is that another resistor? No. So there's three things on this side of the terminal coming away from the item. On the other side of the terminal, I don't really see anything. So three resistors. Oh boy. One of them is 1 million. There's nothing special about these guys. Where does it go? Okay, so it goes to one of the IF transformers. I'm pretty sure that is. So there we are. So this is an easier spot now. So we got a capacitor supposedly to a brown, black, green 1 million ohm resistor to, and I can identify which one of these, which transformer this is. It is transformer number. It's number 2. Transformer number 2. So we'll take a look at transformer number 2 on the schematic. Try to find a 1 million ohm resistor coming off to a couple other resistors and a capacitor. That'll be the challenge here, along with getting my camera to aim the right way. Never mind that camera. He's gone to sleep for now. Okay, so we'll jump on the schematic and do our best to find the terminal on IF transformer number 2 that has a 1 megohm resistor coming off it to other stuff, including a capacitor. Okay, so we're looking at the schematic again, and the IF transformers are up here. This is number 1, this is number 2. So coming off one of these terminals, we should find a 1 million ohm resistor. I don't see one. T2. Okay, well let's look at T1. Maybe I do I'm wrong. Oh, here's a million right here. Okay, and you see the million attaches to this wire, which goes all over the place. Now, here's a capacitor, 0.01. This is probably it, C15, 0.01. This is probably it. Now, why would they use a big fat molded capacitor like that instead of using this? Hold on, we're jumping to conclusions here. So off this wire, which is this wire, I'm looking for, so look, here's another one to ground. Yeah, that's got to get over there. Another 0.01. Gray. Yeah, I don't think this is it. I don't remember a gray wire being involved. So what I'm hunting for is any coil directly connected to this line. There's a diode. There is a diode on the terminal strip. Hit a resistor here. So there's two capacitors off this line that I can find. And I confused myself, haven't I? This one here. There's this guy. He's physically on the schematic located right near the transformer, right near the resistor. On the schematic. And the other one, I'm just double checking everything I looked at. On the AVC line down here. Oh, for crying out loud, I've got a picture I can look at. What am I doing sweating this? Well, here it is right here, for crying out loud. Duh. That's what I get for a late start. So this has got to be it here. Pretty darn sure that's it. C25. Okay, we'll go back to the schematic now. C30. What was this one up here? C19. Okay, here's C25. Now how does that get... Oh, it doesn't get connected directly. It goes through the 1 million ohm resistor. That's this. But wait a minute, no. It's supposed to attach to a 1 million, the other side of which, yeah, it goes up here. There's another million, just to confuse it. Okay, 2 millions. You cross a million right to there. And you find another million resistor in there. So I should verify that this is it. Lots of things. Noise limiter circuit. I don't think this capacitor is really part of the noise limiter circuit. It's just, well, you know what? Maybe it is. I'll take that back. So 0.05 is what it should be. Now that kind of explains the size of that capacitor. I think if they were doing 0.01s, they're using ceramic, little flat ceramic guys. 0.05 maybe get a little big for that. Just glancing around the schematic, looking for other large capacitors. There's a 0.1 right there. 0.1. This is a 0.05 that we're talking about here. Well, this 0.1 is probably one of those green ones. That's probably the state of affairs here. Okay. Now, my next question is this capacitor any good? Is there something wrong with it? Let's go investigate. So it's grounded at one end and the other end is looking into a pile of resistors. So let's put the ohm meter on it first as a kind of a crude check of things here. I'm off to a late start today because I've already started a fire in my fireplace and I've also plowed out my driveway and getting ready for, and it's only about, I don't know, about that much snow. It wasn't a lot of snow out there. But according to the weather report, a lot of snow is coming. Now, I think I said that a couple of days ago and almost nothing hit here. So we're having a weird winter here in Aurelia. Snow piling up around us. This guy. Like if you have a winter without snow, what's the use of having a winter? So we're getting 1.5 megohms. That's almost certainly due to the adjacent resistors and the external circuit. I doubt this is indicating any problem with the capacitor. Okay, let's try another goofy instrument here. Well, I shouldn't call it goofy. This one might be just a little better at measuring in-circuit parameters. I'm not sure. So, what's it say? C equals 60 nanofarads. Okay, think about this. 60 nanofarads is the same as 0.05 microfarads. That's what it's supposed to be, isn't it? 0.05? It's pretty close. 60, 0.05, I think it's 0.05. In the 2.2 V-loss thing, you know, all those resistors hooked up there. Let's just jump right onto one of these. Since I have the meter here. Again, it's in circuit, so I don't know the value of this test, but let's see what it does. Well, capacitor. It's thinking a long time on this one. Can't decide. What's happened? 29 picofarads. Well, that's way off, isn't it? Because this is supposed to be a 0.1. It says right on it. 0.1. 0.1 would be 100 nanofarads. 100,000 picofarads, not 29 picofarads. Did I get these leads on right? How do you possibly get that low a reading when you go across a capacitor like that? How can it be so low? Let's try it again. It took a long time thinking about it, so probably again adjacent components are just making it impossible to measure this in circuit. But as my instructor said in college, watch out for meters. They always give you an answer. 29 picofarads. So they got a really bad capacitor here, which is not very likely because it looks beautiful. And they got a radio that works. Let's try the other one. So this is the last of the three I want to investigate. And it goes to ground, so I can just go right on there. So this is also, I assume, a 0.1. That was pretty quick that time. I just wiggled the leads. Not very reassuring. So in this case it says it's 156 nanofarads. That's a 0.1. Isn't that around 0.1? Look at all these other things. ESR 2.9 ohms. Again, doing this in circuit. So what are we finding out here? I don't really know for sure. What did we find out? We found out this one gives you a really weird reading. I shouldn't do so many things at once. Right. So that one is essentially testing correct. That's what I would deduce from this. It's suggesting it's okay. This one, we have a suggestion it's not okay. Why don't we find out what this guy's doing? Let's find out what he's doing. He's hooked up, oh, he's hooked up to a terminal strip. This is grounded, this end. The other end, jeepers, I just had a heart attack thinking the radio was on. The other end, it goes right to a, looks like it goes right to a tube pin, which is really helpful. Okay, I can see it going clearly to pin number. Pin number looks like what? What does it look like? Okay, so I'm trying to find the bottom of this. There you can see the tube. Practically read the pin numbers there. 1, 2, practically read them. 8. 1, 2. 2 became 8 there when I moved the light. 7, 8. Okay, 9, gap, and then 1. Okay, so the gap, the 9. So it's pin 9 on what tube? Pin 9. Pin 9 on the third tube over. Which tube is that? So pin 9 on the 1, 2, 3 tube. 3 tubes over. Okay, let me sort this out now and we'll look for it on the schematic. Pin 9, 3 tubes over. 3 tubes over. So we are over here, it's this tube. It's V5. It's V5, pin 9. Pin 9 of V5, 68W8. 68W8 is over here. Part of it's over here anyway. 68W8. There's pin 9. Pin 9, there it is, 0.1. That's the guy. So I don't know, why would I hesitate to change it? It's right on top, it's easy to get at. I have an indication that it's bad. The only thing good about it is it looks good and the radio works. What else could I do here to prove it's well, if I'm going to remove it, I can always cut one leg and then test it and then think again. That sounds like a more appropriate approach. The capacitor's good. Why would I want to change it? It looks lovely. That's what we'll do then. We'll lift one leg here. I'll try to preserve the lead. So I have it to solder back. Yes, did I mention we have a visitor cat coming for 2 weeks? Gonna be here in about an hour. This is a bit of a scaredy cat. So it'll be interesting to... Oh! That was bad! I'm just bending the little bent over piece of wire and it just broke and flew off with hot wet solder on it and landed somewhere. And it's probably soldered itself somewhere in here, looking now like any other little piece of wire. Oh my god. Is that it? I don't think so. No, that's not it. It's just a little tiny tidbit. But the thing is, it flew off with hot solder on it. And that's why I shouldn't have done this. Okay. You just seem to never know. I never know what's going to happen here. Let's see if we can get it off now. There we are. Okay, let's give her another test. 0.1, eh? Surprised on the electrolytic one I replaced. Let's see if I'll be surprised on this. get right on the actual lead. There we are. Okay, MK328 Tri LCR ESR tester. Let her rip. So 136 nanofarads is the same as 0.13. ESR 2.9 ohms. And D loss. So I'm not familiar enough with these numbers. I know younger guys doing modern equipment, this is what they live with. But so you know what I'm going to do? I'm going to put the other tester on this guy. 0.1 is a fairly large capacitor, so again with fairly long test leads I can still get away with testing it. I have tested the capacity of my test leads, and some of them are as low as 2 or 3 picofarads, and some of them are as high as 10 or 20 picofarads. Well, that's nowhere near 0.1, so we don't have to worry about additional lead capacitance making a mess of this test. We'll be able to see the actual leakage under pressure on this capacitor, which I like better than okay, so we're set up to put 25 volts onto that capacitor. The rating is 400 volts. So here we go. Watch now. You know, that's not terrifically good. It opened, you know, it could open bigger. Okay, that's only 25 volts. Watch this, 150. Oh, it's really not doing very well. And if we put 250 on it, it's not even, it's just opening a little wee bit. Barely see it in the camera. It's half out. It's half out, it's half worn out. It's coming out. So that's the determination on this guy. He's going to go. I have a 0.1. Oh no. Next problem is 0.1. I don't think I have any 0.1 capacitors. Do I? Maybe I have a lot. 104. I think that's 0.1. .01. ESR 1.9 ohms. It's a brand new capacitor. So see, I don't know what that means. You know what I think it means? I think it means it's the resistance basically in the leads, the contact of the leads to the foil. I think that's kind of what you're getting here. I don't have to believe that at all. 0.01. 104. 0.01, 104. Okay, I gotta figure out what is 104. I had a nice chart of, oh, it's gone. I had a nice chart of capacitance. This is how lazy I am. Rather than look it up and read it, I'm just gonna try measuring it. .1. Look at 0.1 on this. Yeah, I think I got 0.1 on the other one. Didn't I? Am I just confusing myself here, as usual? I think I'm just confusing myself. I think this says 1.98, 0.01. 98. 0.01. Here I am, once again. I'm the guy with 2 watches who doesn't know what time it is. Let's just keep going. Maybe I'm going to learn something by doing this. 2 microfarads. I seldom use this meter for in here, as you can see. I don't know. These leads might not even slide into these slots. Point 1. What's happening with this other meter? I must be not thinking right. Am I thinking right? It takes 100 nano to make a 0.1. I don't know what's going on with that meter. Wow, it's really unsettling. I get unsettled in here all the time. I need 2 of these. Okay, so I'm going to replace this one. And we'll move on to checking the other one. Now, if I look away, I'll forget where that came from. Even though I left a little wire tail there. This is a very busy radio. Sangamo, type 33. So I'm looking for cracks or openings here. Let moisture in. Not much of anything. Some of these molded capacitors will crack right along the seam. They're really bad ones. This is just fine. Okay, I'm going to install this and then we'll carry on here. Okay, so I'm just finishing up on that's a very, very crowded radio. Just lots of stuff going everywhere. Okay, just bend this around here a little bit more. I think it might be wise to test this radio after doing this one, because I will have changed this part down here too. That's 2 parts. I don't want to get too many. As much as I don't think this one which is attached to the relay can cause any real sneaky operational problems. If it causes a problem, it's going to be pretty obvious, I think. But these other ones, either I'm eliminating a problem by changing this, probably very subtle in fact. So what exactly am I trying to say here? I'm trying to say how do you know what you've done has had any positive or negative effect? Hopefully I'm familiar enough with the radio now that any change in its operation will become fairly obvious. Keep the hope alive. Okay, so are we ready to test it here? Got this connected. We still got this plate current, which I think is pretty important. Keep an eye on. We're going to transmit, and we're hooked up to the outdoor antenna. No, we're hooked up to a antenna lead to nowhere right now. It's disconnected at the other end. What is going on here that we would need to transmit? Okay, so we could transmit for just a moment just to make the relay operate, or I put a dummy load on it. That's even smarter. That would be a smart move. Here it is. Let's do that. Put it right on here. Okay, so let's Working into a 50 ohm resistor now. That's good. Good, good, good. Put some tools away here. I'm gonna have to spend an hour straightening up my shop here for sure. Okay, that's good enough for now though. All safety aside. Oh, guess what? Uh-oh, cat is here. We'll have to turn this on in a little while. Cats are running everywhere in this house now. Okay, got the new cat in town. Settled into one of our spare bedrooms. And our other cats are, one's aware that something's going on and has seen the cat. Our other cat not clued in yet that there's another cat in the house. Wow. It's going to be an exciting day. I'm talking about exciting. Let's turn this thing on. Whoops, whoops. Wow. Okay, I almost fell there. Okay, I'm too excited. We've got this for an antenna. There we go. So with this as an antenna, we're not going to hear anything, I don't think. Let's see. The volume up full here. Oh, full power. Add a little antenna. Not much. Okay. Let's put something on it that masquerades as an antenna. Oh, smokes, what the heck was that? That might be... What was that? So the squelch is right at its limit right now. Whoops, didn't mean to do that. Because there's so little signal coming in. Where's my agent key? Let's put this antenna on it. Get a better... Put this on and get a better... Yeah, that's all because of the squelch. Okay. Didn't seem quite normal, but okay. There we are. Now it sounds like a normal CB. It's 5, 13, 15. The squelch has a fair bit of free play in it now. That's good. Okay, well, seems pretty normal. We will now transmit. You know what? I'm going to do it into the dummy load. I just don't want to. Okay, so we should see under 2 volts here, but above 1.3. And what else should happen? Anything else should happen? Volume down. Don't think so. You should hear a nice click on the relay. This is all about testing the relay, really. I saw 2 up here. Interesting. Okay, so I think that indicates everything's okay, and I can continue with the changing of the last, or checking of the last big green guy. Let's turn the power off. That big green guy, now where is he in the circuit? Let's see. So he's got, looks like one end grounded, the lower end grounded, the upper end, it just goes into another network of resistors there. on a terminal. Hey, look at the picture. Look at the picture, Tim. I keep forgetting. This shouldn't be too tough. Let's go check the picture out. Okay, here we are. Now, the capacitor I'm dealing with is kind of down under here. Son of a gun, is this it? C25? I thought that was the Bumblebee one. The two of them are basically installed in parallel, So the one I'm after is in my radio is deep down in here. Look, here's the green one I just did. It's not green in this radio. In this picture. Well, this didn't help much. Let's see. C25 is the one, I think that was the .05, which appears to be okay, or okay enough. Here's C34, pointing at something down here. And that's it. All the rest are something else. C34, let's find C34. There's C34 jumping right out at me here. It's here in the circuit that's related to the squelch a little bit. Squelch control is here, right in the cathode circuit. So, you know what? I mean, that suggests this guy could very well be that. One end grounded, and the other end tied to a network of resistors. So that's got to be it. It's the right size and everything. So can I test this? Let's see, it's 100K this way to a capacitor, and an open plate. The other way, it's 500,000 ohms to where? 500,000 ohms. Oh, gets into all this stuff here. So 500,000 ohms. Yeah, that's pretty high. Yeah, I think we can probably test it. So we try to get where'd it go? There's a point. There's a point one there. 63. That was the other point one. That's the one I changed already. 34. Okay, we're going to go after that. We'll test it. We're realizing that really trying to test components in the circuit is really pretty questionable stuff. Let's start with the meter I've learned to distrust so far. Temporarily distrusting this meter. To ground, I think ground anywhere will do it. And it says, okay, so this says 145 nanofarads. That would be a 0.15 capacitance. It's very similar to what I read on the other one, isn't it? The process with the other one was I tested it in circuit and then lifted one end, and then it became obvious that it was a little bit leaky. Yeah. Wow. Doesn't look like fun going in there, but I'm going to have to get in and nip it. Stick the new one down in there. Not impossible. Okay, I'm just going to nip it and we'll test it nipped. No intention of returning it to the radio since the first one came out a little leaky. And we are on the terminal next to this terminal. The terminal next to this terminal underneath this resistor, underneath this resistor. Attached to a brown, black, yellow resistor. Brown, black, 100K, I think that one would be. Okay, so we nipped off the lead here. See, I've nipped it off in a way I can't, like I didn't leave any tail there to identify where it came from. So realizing that, I could be called away at any moment in the middle of doing this, I'd come back and I'd have zero memory of what I was doing. Let's put this here to mark it. Okay. Of course, if you have zero memory, that means you don't even know you forgot something. How many of us are suffering from that? Of course, I guess you don't suffer from that. If you forget what you've forgotten. 128. Now, it's got that ESR 5.9. My experience has been when you're reading capacitors and they read higher than their rating, it's often because they're leaky and the instrument is thrown off. Is that the case with this thing? I don't know. So we're just going to march down the test instruments here. I enjoy doing this because if you have one instrument, you're well, you think you know what time it is all the time. Let's put it that way. You're comfortable with your mistakes. For crying out loud, I can't do it with this meter like this. This is but we can do it with this one. Up. He's also saying 1.5. On a 1. Okay, well, going with the theory of a high reading, I mean, how can it get more capacitance in it? It's a little hard for me to believe it can get more capacitance in it. Let's use the big guy. We'll do the leak test. So the fact that I have long leads means nothing on the leak test. Okay, that's good. So we're ready to go. 25 volts. Okay, we're set for a non-electrolytic capacitor. Watching the eye. Open, but it didn't open as wide as it could. That's not bad. 25. It's going to be the same as the other one, I bet. 150 slow partial opening. 250. It's a little better than the other one. It's really not very leaky. I'm going to take this capacitor and perform the same test on a brand new capacitor here. This is what a brand new one looks like. Okay, 25 volts. See how it's quicker and it opens wider. 150. Quick, opens wide. 250. Quick, opens wide. So, you know, that's what a good capacitor looks like. Careful now. Just give it a moment here. What did I get up to? 250. So, as I've explained so many times, when the instrument's just sitting like this, it has a short across the capacitors. I'm just giving it a moment to deplete that. So, bad capacitor, I would say. Good enough for changing out. So I'm going to cut that guy right out of there. I'm going to fish it out. How am I going to get it out of there? Holy smokes. No doubt that's one of the first components they put in this radio. Okay. I'll let you watch me get it out of here. How am I going to do this? In the worst case, I can just leave it in there, but looks like it can come out this way. My meter saying, no, 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 don't do it that way. Opinionated meter. No, there's no way. get it out the bottom here. You just kind of push it down behind all these wires and stuff. Why don't you just shut off already? Really? I'm gonna shut off. I'm gonna shut off. Oh, just shut off. Pretty close there. Pull this guy. Can't pull him. Move this resistor. Ooh, ah. Barely move it. So you know, the surgical model of this would be cutting out somebody's appendix and then you can't get it out. It's just laying in there now. Where's it caught? It's caught. So it's hard up on the chassis in the back there. It's the same resistor and capacitor here. Maybe they can't move them anywhere. You get in there with a big pair of wire cutters and smash this part. Even that's... Okay, what if I swing the bottom to the left? Swing it to the left, and now try pulling it out. A new jam up point. How about that? It's a boy! Okay. I say, let's test this guy once again. With him out here. Totally out. Totally free. ESR 2.4 volts. I don't know. Does that mean anything? I don't know. 132 nanofarads, so 0.1 and a bit. And a bit. One and a bit. 0.1. So let's try one more. This is a really weird test. So I'm going to put a short on this while I get another meter ready. The voltmeter. Volt DC scale. Okay, we're going to go from there, and we're going to go here. Better see nothing. Now what happens? Whoops. What happens? Here's the question. So the short lead is off now, the shorting lead. What do we get? 0.3 volts. 0.3 volts out of this thing. Now, it's not the best at supplying current. It's actually going to be able to supply my, I think this is a 10 meg input impedance. Does it say on it somewhere? It's at least 1 meg anyway. It's at least 1. I think it's 10. So, it doesn't take much of a battery to push a bit of current through 10 megohms. But what this tells me is this capacitor has moisture in it. Can anybody else explain that? So if we take a brand new one, this is where my scientific study here falls apart. You'll now demonstrate a brand new one has nothing in it. Nothing. Nada. Nada. Go away. I don't know why that showed up. Yeah, a little static discharge on it just now. But if we take the other big greenie here, okay, again, we put a short on it, make sure it hasn't got any residual. You're going to tell me, oh, it's just residual voltage. Don't think so. Pretty sure if it was residual voltage, then even with the tiny drain from this meter, the voltage would just go down, down, down to 0. It would eventually get to 0. But that's not what's happening. Zero, and I take off the shorting lead. This is a not a very quantified test I'm doing here. This is much less than this guy. I guess too you would get a polarity. See, yeah, there was a 1.5 volts on this thing when I first hooked it up. 1.5 volts. What have they got inside here? So, you know, it's going to be some mixed metal stuff going on inside here. It's going to be probably aluminum foil. And then we have steel leads or plated copper leads, something of that sort coming out of here. There's your two metals. And look it up on the electromotive force scale. You'll find out aluminum is electronegative, very electronegative. That's probably what we have. We have an aluminum copper or aluminum tin or something like that battery here. Hard to believe, eh? Moisture would get in there, but I guess, you know, after decades and decades and decades. Listen, moisture passes through everything. There is a vapor transmission rate for everything except metal. Metal is all that will block water, moisture, or water molecules. And that's why you often buy chips in metallized plastic bags to get that thin film of metal to stop the moisture from going in. So even though these things are molded and all that kind of stuff in thick plastic, nobody thought this radio would be around at this point in time. Nobody thought this thing would be around for even 20 years. They probably figured 20 years. Wow, that'd be fantastic. Here I am so many years down the road with it. And so what does that tell you about all those ceramic capacitors? If I got an old ceramic laying around. So this is the ceramic I took out of it. What did you do with the voltmeter? Bring it back. I've only done this with basically paper and wax capacitors. I've never really done this on anything else. So on the voltmeter, there can't be much of a charge in here of any sort, or much power, so watch the meter carefully. It may just flick up and go to 0. Well, I don't know, you call that a flick up and go to 0? So I'm on the 200 millivolt scale. Is there a volt on that? No. So it must be 1 millivolt. This must be point. I don't know how this works. 200 millivolts. I don't know. No, nothing there. So I guess you could argue that here's a bad actor. So this one, again, just looking at voltage, just picking it up off my bench. So there was a large voltage in there, it bled down immediately on hooking it up to the meter. But I see it won't go to 0. Don't go to 0 now, okay? Prove me a liar. Okay, let's try. I've done these experiments many times, and the results are really pretty consistent. So this is a brand new electrolytic capacitor. Any voltage in that? I think you could argue no. And now I will dig into my drawer of old guys here. Let's grab a weird one here. This is a strange-o. This guy's a real high voltage one, I think. No, 400 volts. 27,000 picofarads. Again, the voltage is in there and bled down almost immediately. So it's suggesting there's moisture inside. It's not really giving me too much information about how much moisture, or is this a dead dog? It's out of a radio. I cut it out. That's why I've got it. So there we are, testing capacitors to death. But that is the approach I like to take. Now we got to stick another 1.1 in there. It's going to be a little easier getting a new one in there than it was getting the old one out. Just take the top off this. Quickly looked over to make sure the radio wasn't switched on. That would be bad. Get close to the terminal. The first one above the other resistor. Getting caught on. Come on, no. Don't go there. Go up in there. Perfect. There we are. Don't fall. Wire here. So what we did with the visiting cat is we put it into a bedroom, whoops, by itself, close the door. He's got his cat bed here. We got it a couple days ago to let our cats smell it, and so he's got his familiar cat bed in there. He's currently underneath the bed, hiding, but that's okay. That's okay. We just leave him alone. He'll calm down, and my wife and I will get him comfortable with us. Okay? He's seen us many times because we go over to visit where he lives. So he's seen us many times. Our cats are a totally different deal. But this cat has had other cats. He's alone right now, but he has had cats in the past, and he was a big-time player. So we're really hoping that's what happens here. He'll because our cats are big time players. Where'd that go? There we go. Like the way I put it in, it is shorted against the next terminal, so we're going to bend. Oh, didn't get soldered at all. That's no good. come it didn't get soldered at all? What was I doing? Heating up the wrong terminal? Yeah, I really gotta get better with these tools. Oh, you can manipulate a wire a lot better. Definitely soldered that time. Bend this wire up a little bit away from the adjacent terminal. There. Now, sure, it goes to ground. Appear to be rushing. Yeah, it's after lunch. I'm hungry, man. I'm hungry. I got a cat to play with. Very good. Right there. Cut the excess here. Grab a wire's too big. I get down on my hands and knees here to do this. Oh, that was great. Just sent my roll of solder going across the floor down here. Oh, for crying out loud. Don't worry about that later. It's like 2 meters of solder played out here. But I have the business end. She's good. Bend that like that. Good. Goody, goody, goody. Leaving that guy, leaving this guy. Okay, let's give it a test. And I'm going to run down. I'm going to set up the antenna so we can actually transmit out an antenna, or at least down the lead wire to the antenna. Okay, I think we're all set here for a real world test. Woo. First find the real world. Okay, turn this on. Full power. So I do not have a watt meter in line here. I'm not too interested in that right now. I'm just interested that the radio still works and the plate current is appropriate and stuff like that. So. Sounds the same. Squelch. Still slow. See, most squelches don't do this, at least this readily. They're usually open or closed. It's okay though. We'll skip 15, 13, 5. Okay, on 13. Watching the plate current, which you cannot see right now. There we are. How come everything got quieter suddenly? What happened there? There we go, watching the plate current, and the plate current is, well, 1.8. Alabama, can you hear me? Alabama! Nope. Alabama cannot hear me. Great. So now I think I'm really at the stage here where it's just one last tune-up. And let me show you something interesting here, which I think is interesting. So here's the Faraday cage cabinet for this radio. Somebody previously punched a bunch of holes through it here for, I guess maybe for mounting this in a car. There's some on this side too. That's the microphone grip there. On the bottom, there are these two things here. So these are obviously access holes to go through the cabinet. The cabinet is sitting basically like this. Through the cabinet to my favorite capacitor and coil. So these are in the output filter circuit, past the power amp, just on its way to the antenna. So what's the deal here? They want you to adjust these when this cabinet is on. And I'll bet you the hint here is when you get this thing all set up in your wonderful CB shack and you got your antenna all hooked up and everything is stable, pop these open and give it a tune. I think that's the situation. And I'm looking forward to it. Okay, I think we're done for today. Thanks a lot for watching, and I'm going to go play with cats. It's going to be a day of cats.